All right. Thank you, all of you, for joining this session. Let me share my screen with all of you. Okay. Sharing screen. Yes. So we are basically revising the questions that we had in the exams. So we basically want to look at how you should have approached the questions. So the first question was that a study was conducted in a healthcare setting and collected data on systolic blood pressure of 100 patients. The mean systolic blood pressure was found to be 130 millimeters of mercury, with a standard deviation of 10 millimeters of mercury. Critically evaluate the usefulness of these summary statistics in understanding the distribution and the variability of blood pressure amongst in the patient population. Okay, so that was the question. The key things here are that a variable was measured, and that variable is blood pressure. Okay, that variable is systolic blood pressure. Okay, now the key measures that were taken were the mean, which is basically the average, and the standard deviation. So for you to tackle that question, you needed to have understood what these two things mean: the mean and the standard deviation. What are these key things? What do they mean, and when do we use them? What is the advantage of using them, and what are the disadvantages of using them? These are the two things that they actually needed: understanding what mean is and its usefulness, and then also understanding standard deviation and also its usefulness. Okay, so that is why the question is that you need to critically evaluate the usefulness of the summary statistics. If you are to remember very well, in my first lecture of biostatistics, I said we have what we call descriptive statistics, and what we call inferential statistics. And you need to know these two, the inferential statistics and descriptive, these two things. If you know these two things, then you are going to be very good student of biostatistics. Now, when we talk about descriptive, we are talking about summarizing data. We are summarizing data. And then here, we are basically in inferential. Our interest is how we make conclusions, on populations based on sample data or based on data from samples. Okay, please make sure you mute. If you don't mute, you create issues for us. Make sure you mute. Okay. So how you create, how you make conclusions on populations based on data from samples. This is to say that if we want to know the prevalence of hypertension in South Sudan, we are not going to measure the everyone's blood pressure. We are going to get a sample, okay, representative sample, and then be able to say that the prevalence of hypertension in South Sudan is between 2.5 to 5%. So that is an inferential, that one comes from inferential statistics. How we describe and summarize that as descriptive statistics. Now under here, under descriptive, we have two major parameters that we are interested in. Measures of spread, or what we call measures of dispersion, or what we call measures of variability. That is one branch of the statistics that we look at. Okay? The other branch is what we call measures of central tendency. So two things that we look at in descriptive statistics. These two things here. So this question is actually under the measures of central tendency. How you see you have, let me explain it here. So you have 10 students with the following scores. The following scores in epidemiology. We have 10 students who have the following scores in epidemiology. Lometa, you have your hand up. You have a question?
Yeah, the presentation went mute. I could not hear anything, and the screen itself was also at the moment
But
closed
it
off.
should be okay right now,
So I
right?
was like, what's happening? Is there a network issue? Yeah, for now it's okay.
Okay, fine. So let's go ahead. So we have 10 students who got the following scores. One student got 34, another one got 56, another one got 76, another one got 80, another one got 69, another one got 75, another one got 80, another one got 92, another one got, how many are they so far? These are three, these are three, these are three, Another one got 56. So you see those are 10 students with different scores in their exams of epidemiology. Now, when we see this data, it does not tell us how similar the scores are. We don't know how different, how the variability. We don't know about how do the values actually differ. We don't know that, okay? So we need the two measures to understand the variability and then the issues to do with central tendency. Issues to do with central tendencies are whether, how close are the values of this data set. And then the issues of this of spread, how do they vary? What are the extremes of this scores or this data set? So we have 10 students with those scores. So if you're going to look at the measures of central tendency, we have 3 of them: mean, median, and then mode. These are obvious things that you studied in secondary and primary. You know the mean, which is the sum over the total number. So you're going to add this, divide by 10, because there are 10 students. You get the mean. Now, what you add upon that mean, like the knowledge that you need to add now, because you know this is what you call arithmetic average or mean, basically. You know how to calculate it, but what does it mean? What does the average mean? Okay, the average means that it gives us information that most of the people are most likely going to score something closer to that mean. So if you add this, can someone tell us the mean here? What is the mean? Use your calculator around there if you have one. Open this. Anyone who has added? So you have 34 plus 56 plus 76 plus 80 plus 68 plus 75 plus 80 plus 93 plus 90 plus 56. What do you get? Anyone who has come up with an answer? You don't have calculators around you?
Yeah, so according to me, it is like 65.2.
65.2. Another person?
Yes.
Yeah, to me. Hello? Yeah, me, I got 708. So when I divide by 10, I got 70.8.
Yes, someone got 70 point what? I have 70.8.
Me, I got 70.8.
Yes, 70.8. So that is the average. Okay?
There 7.08, yeah.
Yes, 70.8. Now, what does the 70.8 actually mean? What does it mean? One person at a go. Yes?
It
Yes,
is
Baiti.
70.8.
Okay.
Yes, Baiti, what does it mean? What does the 70.8 mean?
It is 7.02.
No, it cannot be 7.02.
Okay.
It is 70.8. Yes, Lometa,
Yeah,
what does
yeah,
the
yes,
70.8 mean?
yes.
Okay. To me, that is the average that that population or that total number of
Mm,
persons put under study has been summed up to. So
mm,
meaning a figure of that number
mm,
of that population or that sample number are likely to be measured that blood pressure or develop that blood pressure issue.
Okay, thank you. Another person?
Maybe someone can as
Yes.
well pick from there.
Mm-hmm. Yes, go ahead.
Yes,
Uh-huh.
how together.
Yes, we are together. Mm-hmm.
Yeah. So yeah, so according to me, so it means that this is average of
Mm,
total of the 10 student. So it is like the percentage. It is like the percentage. Maybe assume that if all this mark is for one person,
mm,
then you divide by the total number of the subject. So it is like the average, or it is a percentage of what that person get. So which is like the first mark, and
mm,
it is a mean of yeah, it is mean which is like the center of the total mark that they have scored.
mm. It's like the center mark. Yes.
Yeah.
Okay. Thank you very much. So now I'm going to introduce you to a concept called normal distribution. The concept is called what? Normal distribution. So I'm getting for you a graph here. I guess you can see it here. This is a curve. It's what we call the normal distribution curve. Are you seeing it, all of you?
Yeah, me, I'm
Yes, we are
seeing
seeing.
it.
Okay, very good.
Yes.
Now we have what we call normal distribution. Normal distribution is the shape that you are seeing on the screen. It is what we call the bell shape. It's what we call the bell shape. In the middle, you have equal parts on either side. If you divide it into two, you have equal parts. Okay. Now we have variables that follow what we call the normal distribution. Variables such as height, intelligence, and even um, variables like also blood pressure that we are looking at can fall under this normal distribution. This is to say, let us take the issue of intelligence. If you're measuring intelligence, you have very few people. Okay, this is the number of people on your, this is the right, I mean the y-axis. The y what? Axis. And then this is the variable that you're measuring, which can be height, which can be intelligence on the x-axis. Now, assuming we are looking at intelligence, very few people will have low scores. Most of the people will have the average scores. Most of the people will have the average scores. Let us even take the one for marks. If you are using the marks as the measure, the marks the students get, very few people will get 90s and 80s. So it will be reducing like this, just like you see the curve. You may not even have a student who has 96. You will not also have a student who has 20 something. So most people fall within this category here. They are not getting the highest marks, but they are not getting the lowest marks. Okay? So that means therefore that if you have this in mind, in your mind, that most of the students may not get, for example, in our average, which is 70, it means most people, our curve here will be at 70. The middle part will be at 70. So most of the people will be either 65 to 70 or 70 to 75. And this is what the normal distribution curve means. If the average score for a variable that is within the normal distribution, that is normally distributed in populations, this is what you will get. The curve will appear like this. It will be a bell curve. Well, the meaning of the bell curve is that the mean, you have most people around the mean. Now the distance from the mean is what we call standard deviation. So the distance from here is one standard deviation, which is in a positive angle, to the mean plus one standard deviation, and then the mean minus one standard deviation this side. So if you have the average mark as 70 and the standard deviation as 5 plus or minus 5, it means that 68% of the students will fall within those marks between 65 and 75. 68% of those students will lie under that. So it helps you to predict. It helps you to predict. If, for example, we say that the average height of South Sudanese is 2 meters, it means that most South Sudanese have the average of 2 meters. But in terms of percentage, you know that at least 68% of South Sudanese have the average height of either 2 meters plus 0.5 meters or 2 meters minus 0.5 meters. That is if the standard deviation is 0. Plus or negative 0.5. This therefore helps us in planning. If we know the average, it helps us to plan that, okay, this is how much we need to take care of. So of at least 68% of the people, if you have moved one standard deviation away. So for example, if I'm going to buy, if I have a school and I'm going to buy uniforms for the pupils in the school, and the average waist size is, let us say, 24, I will know that most of the students, at least 68%, will have 24 plus 4 or 24 minus 4. Most of them I'll have taken care of them in that with that simple statistic. So that means for me, I'll be able to buy most of the uniforms will have size 24, and then followed by those that are 20, and then those that are 28, if the standard deviation is 4. So you see that you can make decisions based on the mean and the standard deviation. So when you buy these uniforms of 24, of 20, and 28, no one will say, I don't have a non-fitting uniform, because you are very sure that at least most of them will be taken care of by that simple statistic of knowing the average waist size. Now, if you want to go beyond that, then you also add another standard deviation of another 4. So remember, you have the average of 24, then you're subtracting 4 and adding 4 on either side. Then you can also subtract another 4 from the 20 and add another 4 on the 28. So you'll have 32, and then here you'll have 16, and add a few of them. When you do that, you will know that you have taken care of 95% of the students or the pupils in that school. You will know that all of them will be able to get the size of the uniform that they need. It will be only 5% that may not fit within that. But those will be few, just like the way you see it tempering. So standard deviation shows us how the data is, or a given variable is far away from the mean. But this kind of diagram allows us to predict and take care of situations. So therefore, we go back to our question. If the average mean is 130 and the standard deviation is 10, what does that tell us? What basically we need to do with the question, which tells us to critically evaluate the usefulness of these summary statistics, is the question is basically asking of what importance is the mean and the standard deviation. The figures, the 130 millimeters of mercury and the 10 millimeters of mercury, those ones are basically for you to be able to describe. But basically what they're asking for is of what importance is it for you to know the mean and standard deviation? How does it help you as a healthcare manager? So the explanation is basically what I've given there, but this is what I could have expected you to write, is that the mean is a measure of central tendency. It represents the average blood pressure value in a population. In this case, if you have a mean of 130 millimeters of mercury, it suggests that on average, a patient in the study has a blood pressure of 130 millimeters of mercury. This information helps to provide a general understanding of the typical blood pressure level in the population. You as a healthcare manager therefore knows that, okay, most of the, on a typical day or on average, you'll have most blood pressures around that value. But of course, you can have what you call outliers, which can be abnormally high blood pressures or abnormally low blood pressures. So it gives you a general understanding. In real management, you will see later on, basically using the example that I've given, that you can use the mean to be able to know what did you need to purchase and what you don't need to purchase, and maybe how much. Okay, now the standard deviation gives you the variability or the dispersion in the data. This therefore means that it indicates that the systolic blood pressure values in a population tend to vary. That means that you will not get similar values always, but at least most of them will be either minus or plus 10 millimeters of mercury. Okay? So by considering the mean and the standard deviation together, what does it tell us? The mean, along with other measures such as the median, which can provide us with the information about the shape of the distribution, which we have just looked at here. Normal distribution, and the shape is bell-shaped. Okay? It suggests that this data is normally distributed, which I've explained, the normal distribution. The standard deviation allows us to see how variable are the values of the blood pressures around the mean. Okay? This therefore means if you have a standard deviation of 10, it indicates that the blood pressure values, most of them fall within either plus or minus 10, this point here, of the mean, which therefore means that most of the people will come to the hospital and their blood pressure, systolic blood pressures, will be between this. Because remember, the average was 130 millimeters of mercury, okay, 100 millimeters of mercury, and then the standard deviation of 10. That means that here you can, the 130, you can subtract 10 from it and then get 120, or the 130 plus 10, and then you get 140. Okay, so therefore the 68% of the total population of any of the population will have values between that, the range. Most of them, 68%, will have systolic blood pressure ranging from that to that. That's the meaning of that, of that standard deviation. In relation to the mean, so if you have a greater standard deviation, it means that the data varies greatly. Okay? It means that the data is not similar. People are not having similar blood pressures if you took them. Okay? This information is very, very important in statistics, because you can make a number of assumptions and then be able to make decisions on what you need to do. So on this, therefore, it means it can allow you to know what do you need to purchase to be able to capture the blood pressures of this range. You know what, in a health facility or in a clinical setting, blood pressure readings are affected by the size of the blood pressure curve. They're also affected by the type of blood measurement, blood pressure measurement that you take. The type, is it digital? Is it manual? Okay, so you can make decisions based on some of these values. I remember one of the examples I gave was on how much do you need to purchase if you know the average consumption and you know the standard deviation. I remember posting that kind of question on the WhatsApp group for health sciences students, and I think one of you got the answer right. But basically, the explanation lies on these concepts. Okay, so this question number 1 needed you to explain the importance of the mean and the standard deviation, which I hope I've tried to do. Do you have any questions? Yes, Lometa.
Yes, thank you so much. This really looks very beneficial. Otherwise, uh, with your explanation, I can see a picture of understanding in me. Now, my question here is
Mm,
uh, just like you explained about adding and subtracting
mm,
the deviation, the standard deviation from the given figure or the mean.
mm.
Does it mean every question that requires that talks about means and standard deviation, it's imperative to do so?
Not necessarily. Not necessarily. With the biostatistics, you need to understand the concept, and then be able to relate it to a practical situation. Okay, so there are many scenarios where the mean and the standard deviation can be twisted, but the concepts basically remain almost the same. You just need to know how to connect them. So, like for example, in this case, they combine the mean, which is an example of measures of central tendency, and then the standard deviation, which is an example of measure of dispersion, or what we call the measures of spread or measures of variability. So it depends on how they can relate the mean and then standard deviation and other things. Your role is to know the different measures and when do we use them. In this case, we have known the mean, and we have said that the mean tells us that most people have a value which is closer to the mean. Now, if we bring in the standard deviation, it helps us to know how the data is actually varying. How far is a given data value from the mean? If you have a standard deviation of 1 from the mean, it means you have moved plus 34% and then also minus 34% on the other side, on each side of the curve. Let's go back to the curve here. If you have moved the one standard deviation, it means you have moved that one standard deviation either on the right or the left carries 34% of the population that you have looked at. So that's why you have this combination of 34 plus 34 to get 68. So within one standard deviation on either side, if you add the two, it means that you have 68% of the population will have values that are within minus or plus one standard deviation. And this helps us in planning, just like the example of the waste, the uniforms that we have. But it can also be applied in many different situations in real practice. Now let's move to question number 2, which I think brought a lot of issues. This one here in clinical trials. Let's first move to question number 3, because question number 3 is much more easier, and you see why. So here, this one is straightforward, which is basically calculating the odds ratio and interpret the values. Okay, and it was clearly stated that you have a hospital that wishes to investigate the association between a specific genetic maker and the likelihood of developing a certain disease. in a sample of 500 patients, 100 were found to have a genetic marker, and 80 of them had the disease, and then 40 without the genetic marker, and then on the 60 had the disease. Calculate the odds ratio. This one, if you put the formula for odds ratio, you get the answer straightforward, and then you make the interpretation. Okay, which the interpretation is basically following these three things. If you know the formula right and you did everything right, the interpretation is about these three things. So you just have to choose one of them. But for those of you who are unaware, here you have what you call a 2x2 table. Let me get it for you. A 2x2 table for odds ratio. 2x2 table for odds ratio. Just get that table and then put the things there, and then you get your answer, and then boom, you have the what? You have your marks. This one, everyone should have gotten these marks. If you fail this one, because you only had the 3 questions, I don't know where you're going to get the marks from. But basically, this is what we call a 2x2 table. Okay, so here you have exposures, which in this case is the genetic marker. So you have the genetic marker. So there are people who have the genetic markers and they have the disease. How many are they? Look at the question. They have the genetic marker and then they got the disease. How many are they?
Yeah, 80.
They are 80. Yes. So you put your 80 under A. Okay? You put your 80 under A. You draw that table roughly on your whatever you're doing. Put the 8 there. And I mean the 80. Put the 80 there. And then those who do not have the genetic marker but have the disease, how many are they? This is C. They do not have the genetic marker but have the disease. How many are they?
They are
60.
they are they are 60.
Okay. Now, those who
Yes.
have the genetic marker but do not have the disease, how many are they?
They are 20. They are 20.
Someone is saying 20. Another person?
Now 100.
Let me repeat the statement. They have the genetic exposure. Okay? But they don't have the disease.
80% had the disease, but it is 20 but had ninga by genetic marker.
Yes, it is 20. All right. So we move to the next one, which is D. They do not have the exposure. They do not have the genetic disease, and they do not have the genetic marker, and they do not have the disease. D.
340.
300.
340.
340. So you have your A, you have your B, you have your C, you have your D.
40.
Yes. So you put your A times D. Okay, A times D. You already have your table there. So you this one times that, and then B times C. So when you divide that, you get the answer. Okay, so which is here, which is 80. If you can see here on my screen, you have 80 divided by 20 divided by 60 divided by 340, and the answer is 8. Okay, so the interpretation is as follows. These are the general interpretation issues. Okay, if you have a ratio of 1, it means that the exposure is not related to the health outcome. That means that there is no relationship between, there is no association between the genetic marker and the disease. If you get a ratio of 1, that's what it means. If you get a ratio of greater than 1, it means there is a positive association. That means that the presence of the genetic marker increases the likelihood of having the disease. So if you got anything above 1, our answer actually suggests that we have 8. So it means the genetic marker increases the likelihood of getting the disease. If you get the answer less than 1, 0 point something, it indicates a negative association. This suggests that the genetic marker decreases the likelihood of having the disease. In our case, it means that the genetic marker increases the likelihood of getting the disease. So that is what I expected you to write in that question. So let's go to question number 2. Do you have any question there? Before we go to question number 2, odds ratio should be straightforward. Just get the formula, feed in. The interpretation, if you have above 1, it means the exposure causes the disease, it has an association with the disease. If you have less than 1, it's the reverse. If you have 1, it means there is no association. So let's move to question 1. Do you have any question? I mean question 2. All right, so let's go to question 2 here. Okay, there's a hand. Yes, Lometa. Lometa, you have your hand up. You can speak.
Yeah, I have a question, especially on the table issue. The table actually is well read and is somehow clear. And then now the issue is coming on the calculation of the odd ratio, where I am seeing A slash B divided by C slash D equals to A D over BC. Now, like, okay, the figures, if, sorry, if we're to put those figures, like A, actually the meaning of A slash B, are we dividing A divide by B, and then we divide C divide by, sorry, A divided by B, and then C divided by D equals to A times D and B times C? This
Okay,
is
just a
somehow
moment. Let me connect
not clear to me.
my laptop to power.
Okay, okay.
Okay, so now the key thing here is that we are calculating the odds of the event in the exposed group and then the odds in the event of the non-exposed group. This is basically what we are looking at. So this interpretation, A divided by B and then C, divide the whole of that, divide it by C divided by D, divided by D. What you have here and then what you have as A times D divided by BC is just a simplification. There's nothing much in there. It's just a simplification. So even if you don't remember this, just remember A, AD, and then BC. You remember what we have in describing the ancient times before Christ and after Christ. This is a simple way to remember. AD, if you remember, 100 years AD,
Yeah.
and then maybe 200 years BC. If you can remember that, it is very easy for you to recall. But basically, this does not give you a different answer from this. The whole point is that we want to see those who are exposed, how many have got the disease? That means what are the chances that they got the disease, of getting the disease in the exposed? And then what are the chances that you get the disease if you are not exposed? If whatever answer that you get, you can make any interpretation that you get. Okay? But A divided by B, the answer you get, divide it by C divided by D. There's nothing in there. But this one is easier to remember. AD and then BC, if you remember that history. And it is much more easier this way. Okay? But it's basically cross multiplication. This, like with that. I hope you're seeing my cursor. You can see my cursor when I move it across. It's a cross multiplication. If you have a very good 2x2 table, you will never get this wrong, because you know that it is A times D and then C times D times B. Okay, so there is another hand, I think. Yes, Jansuk, you have raised up your hand. I think I had gone off for some few minutes.
Yeah, I think the network is not all that nice, but maybe to add on something from my colleague about this abbreviation of the odd ratio. The A divided by B divided by, again, over C divided by D is the same as AD divided by BC. It's just the same thing, but this one, the second one, the AD divided by BC, is in a simplified way, a simplified mathematics.
Yes, very good.
That is what I can add on.
Yes, exactly. Thank you very much.
Thank you, gentlemen. Thank you so much.
All right, so we move to question number 2. Okay, so here I tried to put a lot of theory first before we go to the real concepts. So let me first go to the theory before I even go into the details of the calculations here. So the question is that in a clinical trial, if you hear the word clinical trials, just know that we have what you call the treatment group and the control group. But in this case, we have 2 treatment groups. That means that we have 2 treatment groups. That means that we are having an intervention in group A and group B, and then compare what happens. It's not like the usual clinical trial where you have the treatment and the control group. Why do we carry out a clinical trial like this? You could say that you have a drug X and drug Y. Both these drugs can reduce cholesterol level, but you want to choose which drug works much more better in reducing cholesterol level. That's why you do a clinical trial with 2 treatment groups, and then you compare the effectiveness of the drug in reducing the cholesterol level. Now, so let's go to the theory before we come to the calculation. The first concept that we have is what we call the effect size. And this is what I always want you to do when we are faced with such a question. When you're faced with such a question, underline the key terms. Okay? So the key terms here is Cohen's d, that one, and then effect size, that one, and then of course clinical trial, which I've explained a little bit, and then this one, treatment groups, that, and then another one, this one here, and then we also have a mean, because we have the means. The word mean has been used several times. Okay, so those are the key concepts. We have already explained the mean in our first question. So, and then we have also explained standard deviation in the first question. So I started with effect size. Now, effective size is, for example, you want to see if a drug can produce the effect that you want. But that effect should be of a given magnitude for you to say that, okay, this drug has an effect. Let me repeat that. You give me a drug for reducing my body temperature. Okay? So you give it to me, and then after 1 hour you come and test and check my blood pressure and my body temperature, and you see that it has reduced. But are you sure that the temperature has reduced because of the drug that you have given me? You're not very sure. It could be that the thing that had caused me fever has gone. It could be something else. It could be that the room temperature has been reduced. It could be that I've switched on the AC. It could be another thing. But if the magnitude or the strength is at a given level, then we can say, oh, this could be linked to what we are saying. This could be linked to the drug that we are investigating. And therefore, it can be useful in investigating it further, or even in a practical situation, practical application. That's what we call effect size. Okay? It is a statistical concept that measures the magnitude or strength of a study's observed effect or relationship, which I have said in this case is, if you give me a drug, is the drug reducing my body temperature to a level that has significance that can be applied, or the body temperature has reduced because of other issues? So that is what I've tried to explain here. Okay, so it is very important that we understand the concept of effect size, because it provides us a numerical value that represents the degree to which variables are related or how much they differ. And therefore, we can be able to quantify the strength of the effect and determine whether it is large, moderate, or small. If it is small, then it is negligible. It cannot produce what we want, so we cannot apply it in user situation. But it also allows us to compare. Effect sizes can allow us to compare different studies in different populations. And then if we if we see some very good pattern, then we can be able to make very good conclusions. Therefore, effect size is very important in clinical practice. If you listen to BBC or other radio stations, you will see them announcing that there is a potential for this drug to work, but the studies are yet to produce conclusive findings. It could be because the effect size is not that very important, very significant to allow even practical significance. It also allows us to do what we call power sample size calculations. You see, if you have a drug X and you think it reduces temperature, if you have a smaller sample size, you will not be able to detect that change in temperature if you use that drug X. Therefore, it becomes very difficult to have what you call effect size to detect the effect caused by the drug X on blood temperature, on body temperature. And therefore, effect size is very important in determining the power of a given sample size. So that's point number 4. Now let us link the effect size, which I've just explained, to different measures. Okay? Commonly, we can determine the effect size using Cohen's d, or we can use what we call correlation coefficients, or Pearson's R, or E.g. Pearson's R, which is an example of the correlation coefficients. We have other measures too, but in this question in particular, the interest was to use Cohen's d, which we highlighted here. Okay, so we are saying that effect size can be determined by these methods, but our interest is on this Cohen's d. Okay, so what is this? Let us assume you have these values. You're testing a drug X and drug Y. So you have drug X and then drug Y, 2 drugs. You're testing their impact on reducing, let us say, blood pressure, systolic blood pressure. That is your interest. Okay, I guess we are still on the same page. So you have 2 drugs that you think have an impact on blood pressure. So you have the following values. 120 so you're testing it on 5 patients. Each of the drugs is tested on 5 patients. So you have that. The first patient has that reading. The next patient has that. The other patient has one, like that. And then the last patient has that. And then for drug X, you take the blood pressure, it is 130. Another one is 125. Another one is 135. Another one is 98. And then the 50th one is having 95. Now, when you look at this, if you look at these figures like this, they don't really tell you anything. But they can tell you something in terms of average. So here, I don't know what the average is. Maybe someone should calculate it for us there. Calculate the average systolic pressure for that. For the drug X, it's 130 plus 125 plus 135 plus 95, 98 plus 95. Divide by 5, 116.
116.6.
The second patient, the second group, I mean, not the second patient. So you have 120 plus 110 plus 105 plus
119.4.
19.4. Okay. Divide by 5.
119.4.
119.5. Okay. 19.4. So which drug is working? Which drug is working better?
I think it can be
I think drug
Y.
X works better.
Drug X works better because we
Drug
are
X works better.
yes, because we are interested in reducing the what? Blood pressure. That's our interest. So it appears that drug X is better. So this is one point that you need to understand, that if you have values just like the way we had them there, they don't mean a lot. They don't tell us anything if we have not summarized them. So that's why this is a mean, is a descriptive statistic, which is basically a way of summarizing data. So this tells us more information than having these values just written there like that. Okay, so this tells us that drug X is better than this. But that is not the interest. That's not the only interest that we have. Okay, the interest that we have is to calculate using Cohen's d. So how do we calculate that? The first step when you're calculating Cohen's d, which is basically what is required here in the question, using this information, calculate the standardized effect size d, using of course that Cohen's d, and interpret the meaning in the context of the study. And we say that Cohen's d helps in measuring the effect size. So we are calculating Cohen's d. The first step is to get the difference between the mean of the two groups of people. So in our example, where is that example that we had? I hope I think I removed it, where we had the 19 and the 16 already. Let me see if I can get it back. Yes, here. It means you get the difference between, if this is B and another one, A, which is assuming this is group B, which has the 5 patients, and then this is group the group A, like that. Let me highlight this. So get the difference. So in our examination question, we have the mean of 20 for group A, and the mean reduction of 18 in group B. Okay, so that means you're going to subtract 20 minus 18. So that's the first step in calculating Cohen's d. This one here, highlight this, and we did it in this example. I did it somewhere, which is this step number 1. The mean difference. Calculate the difference first. That's the first step. Quest? Are we together there? Step number 1 is done. Are we all together?
So you actually, network took you just a little bit silent. I couldn't get you. I don't know if the rest of my colleagues were getting you, but for me, I was really locked up by network.
Okay, the other people,
Could you
were you
please
getting me?
try to go over again?
Okay. We had our initial
Yeah,
calculation.
we had. Okay.
People are getting off the session. I don't know why, but I hope
We are together.
this was the very important question that we need to deal with. I'm saying we have what you call effect size. Effect size relates to a statistical concept that tells us the magnitude of the effect of what we are investigating in a population, such that we can make a decision whether it is of practical significance or it's something that we should leave because it doesn't give practical significance. Have you understood that concept of effect size?
Yeah.
Yes.
Okay, very good. Now, having understood the concept of effect size, we are saying that Cohen's d is one of the ways of determining effect size. And now we are on step 1 of determining Cohen's d. And that step 1 is you get the average of one group minus the average of the other group. Okay? So you get the difference of the mean, which in this case, one group had a reduction of 20 milligrams per deciliter, and another had a reduction of cholesterol level of 18 milligrams per deciliter. And you have a difference in the mean of 2. The next step is to calculate what we call the pooled standard deviation. The pooled standard deviation, just like the word pooled, it means that you have put the standard deviations together. Okay? So the standard deviation of group A plus the standard deviation of group B. Okay? But for each of these, you're going to have to square them. So you have 25 squared plus 4 squared, okay? That divided by 2. So you will have the 25, which is the square of 5, and then the square of 4 is 16. Okay? Remember, whatever answer you get, you will have to get the square root of the answer that you have gotten. But remember that you have it divided by 2 here. So this is just basically what you see. The subsequent steps are the substitutions and the answer that you have here is 4, which is the pooled standard deviation. The first key thing you need to note is that you first get the mean difference. After getting the mean difference, calculate the pooled standard deviation. Okay. After calculating the pooled standard deviation, now you can feed that into the formula for Cohen's d, which is that the mean difference divided by the pooled standard deviation. And then the answer that you get is this. I don't know whether, do we have anyone of you who got this answer? 0.0, 0.41, 0.44. Anyone?
Yes, I think I got it.
Oh, then you extremely very good. Yes. So if you got that answer, then
Not really.
Now you go to the interpretation, because the second part of the question here, we go back. We go back to the question. Second part of the question. Interpret. So we go to the interpretation. If you got a figure, what does it say? Okay. So in the context of this study, Cohen's d of approximately 0.44 indicates a moderate effect size. It suggests that the mean cholesterol reduction in group A is about 0.44 standard deviations higher than in B. This difference, although statistically significant, may not be considered large. The interpretation of effect size depends on the field of the study and the context of the research question. So what hypothesis are you testing? What drug are you actually testing? And many other factors. This means that the interpretation of Cohen's d is not straightforward like what we had in odds ratio. You get above this, it means this. You get below this, it means this. You get 1, it means this. Here, it means you have other factors to look at to determine what Cohen's d may actually mean. So I've not gone into the more details of Cohen's d, but in this presentation, which I'll be sharing with you, I provide more examples on understanding the concepts of Cohen's d. But basically, that question required you to understand that the means can help you in determining whether the drug that you're investigating, or even the intervention, whatever it is that you're investigating, is having an impact. Okay, and how do you measure that impact? Which is basically, how do you measure the effect size? Cohen's d is one of them. And what are the steps of calculating Cohen's d? Get the mean difference, and then calculate the pooled standard deviation, and then make the interpretation. I have another part which has the explanation for the further interpretation around here. All right, so let's stop there, unless you have